Right, so we are on page 118 in your notes. Starting on permutations today. Right, so this is pretty much an advancement of the probability that we've been doing, okay? The last lesson, or Wednesday last week, we looked at fundamental counting principle. Okay, so event A can occur in A different ways, event B can occur in B different ways, so forth. We simply multiply all the possible outcomes together, okay? So for example, the first example we've done, the Carly owned 5 shirts, 3 shorts and 2 shoes. How many different arrangements are possible for what she can wear? 5 times 3 times 2. Okay, that's basically the fundamental counting principle. We also looked at factorial notation. Okay, in terms that we have a number with the exclamation mark, which is the notation of factorial. And basically we are multiplying that number down by 1. Go down by 1 and you keep multiplying that number. So we had 5 factorial, for example. It would be 5 times 4 times 3 times 2 times 1. Okay, and we did a couple of examples with those. Right, so what we're going to be looking at is permutations and combinations over the next couple of lessons. We'll incorporate our factorial notation. Okay, so we're reading on the notes on page 118. Right, so read. So we start with n different objects and we choose r of them, one after another. Okay, so which is an ordered sample without a replacement. Okay, so we've got a specific order and we are not replacing back what we picked out. Okay, so for example, we're picking out a marble out of a bag and it's not getting replaced, and then we're going to pick out another one. Okay, so putting it simply, but we're going to obviously go more complex in the scenario. Okay, so since the first object out, so the first marble out can be chosen in n different ways. Okay, the next marble out can be chosen n take away 1 different ways. And the next one following that will be n take away 2, resulting from the number of marbles that are left in the bag. Okay, and so on. Alright. So, in the notes, this can be done in n. Remember the dot means multiply in this context. Alright. N take away 1. N take away 2. Alright, times times n take away r plus the 1. Okay? Now, the reason why that has to be set that way is because r can equal n. Okay? So, for example, when we pick that last object, okay, so there's only 1 marble left in the bag, we're going to have n take away n, okay, which simplifies the expression down to 1. So we're making sure that there is a 1 in that box, in that bracket, sorry. So, in other words, we have found the number of ways of arranging n objects at a time, okay, and this number is written as notation n, p, r, okay, p for permutation of a total of n objects or outcomes, and r is the number you need in a specific arrangement. Alright, that'll become clearer as we do some examples. Okay, so in the special case where r is equal to n, we are dealing with the total number of arrangements or permutations of n distinct objects. So, in other words, n factorial, which is n, p, n. Alright? And again, that'll become clearer with some examples. So equals n multiplied by n take away 1, multiplied by n take away 2, 3, 2, and 1. Okay? You can go back to our factorial notation. Right, so the first box there, it says for R selections from n objects with repetition. Okay, so that means we can replace, so we draw the marble out of the bag and we can replace it. Okay, the number of possible outcomes will be n times n through r times, okay, which will then simplify down to n to the power of r. Alright, let's look at some application of that. Right, example A. There are 4 cards numbered 1, 2, 3 and 4 placed in a box. Okay, so a card is chosen, viewed and replaced. Okay, a second card is then selected and viewed. We need to find out how many possible 2-digit numbers there are. Okay, so arrangements. So we need to work out the maths here to be able to tell me how many possible 2-digit numbers we can form with the 4 cards that we draw out of the box with replacement. Okay, so when I take the first card out, okay, how many different arrangements are there? There was...
When you take the first card?
Yep.
Wait, you have to make 2.
No, you take the first card out of a card of 4, box with 4 cards in it. So how many possible arrangements it is for me to draw out that first card? 4, okay, because there's 4 things I can pick from. Okay, it then gets replaced, okay, and then I draw a second card. So that second card, how many arrangements are there? It's been replaced, remember? So it's been put back and drawn again. Okay? So to work out the number of 2-digit numbers that we can possibly draw, okay, we consider how many arrangements there are for the first number drawn. Okay, now because of the replacement, that means there will also be the same number of possible combinations for that second number to be drawn. So, in other words, it is 4 squared. That means there are 16 ways, or 16 2-digit numbers we can form when we draw out 2 cards with the numbers 1, 2, 3 and 4. Okay? Now, very briefly, going back to, have you done tree diagrams before? Okay, so let's look at it from a tree diagram perspective. So you have 4 cards, 1, 2, 3 and 4. Okay, so when you draw out that first card, you can have a 1, 2, 3 or 4. Okay, and then that card is replaced. So when you draw out the second one, you still have the same 4 outcomes. Okay? So there are 4 numbers that we can form that starts with a 1. Okay, so we have 11, 12, 13 or 14. Okay, so there's 4 outcomes here. Alright, if we go through the branches, okay, hopefully everyone will be able to understand that the same 4 numbers will be there. In other words, there are going to be 4 arrangements there, 4 arrangements there, and 4 arrangements there. Okay, and then simply add all your arrangements together, you have the total as 16, or the sum of those is 16. Alright, now remember, if this card is not being replaced, okay, we're going to have different numbers involved there. Okay, but we are taught, you're told specifically in the question that you have replacement. So that's why the possible arrangements will be larger. Right. So that's just a little side example. Okay, so this is what we're focusing on this lesson. So page 119. So when the given objects are arranged in a definitive order, okay, so in other words, I need the number 1 first, followed by the number 3 because I need the specific number 13, for example. Okay, that follows a set order. okay, which is different than drawing a 1 and a 3 in any order we like, as long as we get those two numbers. Okay? So this is a topic where it's really you have to think through your problem and your scenario and logically, best you can, work it out. Okay, so when we have an arrangement of objects or in a definitive order, okay, it is called a permutation. Okay? So when we have things in a set order, we're going to have a permutation. Right, so permutation, NPR, okay, so that's our one notation we need to get used to. Okay, which is equal to, because in your note, n factorial over n take away r all to the factorial. Now, if you all get your calculators out as well, we'll be able to do that on your calculator. Alright, so above your multiplication and division sign, okay, so specifically now we're looking above the multiplication sign, we have NPR, okay, so that's the button you'll be accessing through this particular section. So what you'll need to do is push shift, then that button to be able to use it. Okay, and we'll look at an example shortly on using that. Alright, so let's do a proof. Proof 13.2. Okay. So our NPR, okay, so going through your factorial notation, is equal to n times n take away 1 times n take away 2, right, times dot 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 n take away r, whatever the values for n and r are, right, because it will stop at a specific point. Okay, for example, if there were 8 people to line up in a straight line, how many ways can we arrange the first 3 people? Alright, and that's where the incorporation of the r value comes in there. Okay, instead of considering all 8, which is 8 factorial, you're only considering the first 3, for example. Alright, we have 1 to that. Okay, so that's the notation for using your factorial notation up to whatever you value for r is. Okay. Screw that. Right, so we're going to multiply this by the official factorial notation you've been told. So continuing on this pattern, okay, so we're taking away 1 as we're multiplying through. Alright, so if I take away 1 from this expression here, I'm going to have an n take away r. Okay, if I go to the next term and take away 1, the n take away r, take away 1, or plus 1. Right, so I'm continuing to decrease by 1 right through. The next term will be n take away r, take away 2. Alright, dot 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 3 times 2 times 1. Okay, all the way down to 1, continuing on with my factorial notation as if it was n factorial through there. Okay. Right, now because I've multiplied by this, I also need to divide spoil that. N take away R, N take away R, take away 1, N take away R, take away 2, dot, dot, dot. 3, 2, and 1. Alright, so what's on the top of this fraction here, I'm also putting on the bottom. So in a sense, we are multiplying this expression by 1. And in order to introduce that, okay, this will get me into the formula that I'll need. Okay. So, I hope I'm not speaking too foreign language to you. So, considering now the top line, we've got N take away 1, N take away 2, N take away R, N take away R, take away 1, right through to 3 times 2 times 1. So this is the notation top line of doing N factorial. Okay, and then on the bottom of the fraction, over there, I'm starting at N take away R. I'm then multiplying by 1 less right through until I get to 1. Okay, so this is N take away R factorial. Right, so if you didn't quite understand that, that's okay. You need to know the result back. Right, so there's your formula up there, and that's number 1, and number 2, the special case, when we have n, p, n, and that will be n factorial. Okay, so we have 8 people, we're going to arrange them in the line. How many ways can they all be in that same line? Okay. So 13. Okay, so N, P, N. So all I'm doing is in the formula that I've done here, I'm going to substitute N for the letter R. Okay, because that will be the R value, which is the same value as the N at the start. So it'll be N factorial over N take away. So I'm replacing this R with an N factorial. Right, so N factorial over, hey? Yeah, 0 factorial, 1. Right, so N factorial over 1, which is N factorial. Right. So like I said, this will become clearer once we do some examples. Right, so while a couple of people finishing up, note that for this topic, you won't always find it practical to use formulas, okay? And there'll be a couple of examples that I'll be doing today where we'll be looking at that, okay? Often it's the case that you'll be drawing diagrams, thinking through logically, and then coming up with some pattern to be able to work out the number of arrangement, okay? So you won't always be using the formula. Okay. Sorry? Do I ever get sick of? You won't be seeing a lot of tree diagrams either, okay? Not until probability next year in mathematics. Alright, so let's look at some examples, make this clearer. Alright, B. We want to find the number of ways, 3 books, that can be selected from 7 books and arranged in 3 spaces on a bookshelf. Okay, so we are now picking 3 specific books. Okay, or we want to consider only the order of 3 books within 7 books on a bookshelf. Okay, so the arrangement. Right, so the total number of books we have is 7, and that will be your n value. Permutation, we have a specific order. Alright, so this will be a permutation style question. And then from those 7 books, we need to have 3 of them considered in that order. Okay, now on your calculator you need to push 7 first, then shift multiplication for the p, for permutation, and then after that p you push 3. So you have, on your calculator, you'll have 7p3 equals
210. 210.
There are 210 ways 3 books can be arranged from 7 books onto a bookshelf. Okay, now this is really the same as 7 times 6 times 5, isn't it? Alright, can we do 7 times 6 times 5? Because the first book can come from 7 books, the second book can come from 6 possible arrangements, and the third book comes from 5. So it's almost in a sense doing your factorial notation, just not all the way through. Okay, so in other words, it is also equal to the total number of arrangements. Okay, so I can have 7 factorial ways I can arrange 7 books onto a bookshelf. Okay, and then I am only actually considering 3 of them, so I'll have to take away the other 4. Alright, so I'm not considering the other 4 notation. Okay, which is from our arrangement, so NPR, which is n factorial over n take away r factorial, so 7p3, which will be 7 factorial over 7 take away 3 factorial. Okay, and that's how the formula works. Right, so this example, we can have just done 7 times 6 times 5 and we get 210. Okay? However, when the arrangements become bigger and more complicated, okay, this sort of question would be handy to use the formula. Okay? But not always. Right, see? Right, how many 4-digit numbers can be made from the digits 1, 2, 3, 4, 5, 6, 7, 8 if repetitions are not permitted? Okay, so when repetitions are not permitted, we have a permutation because we need a specific order of our numbers. Okay, we could ask for a 4-digit number, so you're asking for specifically 1,526. Okay, which are the digits in a specific order to give that specific number. Okay, so arrangements or combination. Oh, I don't like using the word combination because you'll be doing combination next lesson. Right, so how many total numbers do you have? 8. 8 in total that you can pick from. And then from that, you only want the first 4 numbers. Okay? So it'll be an 8p4. Okay? Which is really the same as 8 times 7 times 6 times 5. So that first digit can be picked from 8 different ways. The second digit can be picked from 7 different ways. The third digit from 6 different ways. And the fourth digit from 5 different ways. Now we're only considering the first 4, so that is where we stop. So 8 times 7 times 6 times 5 would be 1,680. Okay? D. Right, in how many ways can 6 girls and 2 boys be arranged in a row? if we have the following condition. We have the two boys together. Okay, part I. So this is one example where the formula is not going to be so straightforward to use. Okay, so instead of a formula, we're going to do a diagram. Okay, so to do your diagram, you are considering the scenario and drawing something that represents that. So we have in this question, we have how many ways can 6 girls and 2 boys be arranged in a row? So in other words, we are looking for the arrangement of 8 people in a line. Okay? Now, I've picked circles because it's much quicker to draw circles than it is to draw rectangles or something. So? Yes, all right, so when we have the 2 boys together, all right, we need to consider them as one. All right, so this style question, we are considering them as 7 people in a line, and then considering then the order of our 2 boys. Okay? Right, so in other words, if we consider the boys in one spot, not smiley there. Alright, so if we consider the boys in one spot, we consider them in 2 positions and then class them as 1. However, in that order, the boys can have an order as well. So there's 2 different ways we can have the boys together. So, in other words, we have arrangement. So, there's 7 factorial ways all these 7 people can be arranged in a line. And the boys can then be considered in 2 factorial, technically, arrangements. Alright, so if there were 3 boys, there'll be 3 factorial arrangements. Those 3 boys can be lined up. Okay. Now, this is the same as 7p7. Okay, how many ways can we arrange 7 people in 7 places on a line?
5,040.
Yep, and then we have the 2 factorial ways the 2 boys can be arranged in those specific spots. Alright, so 5,040.
1080.
Oh, sorry. 10,080. Alright, so the 2 boys are together. Part 2. The 2 boys are not together. Okay, so in other words, there's at least 1 girl separating the boys. Alright, how am I going to work this out? What's the complement of 2 boys not together? What's the opposite of 2 boys not together?
Oh,
What's the opposite scenario to having 2 boys not together? 2 boys together. Okay, so 2 boys together there. The opposite of that would be they would not be together, which is called the complement. Yes?
Yeah.
Right? And you just worked out the arrangement of the number of boys together. Okay, so instead of going through and working out all the possible combinations, use the information you just got. So, how many ways can 8 people in general be arranged into a line? Okay, all the possible ways 8 people can be lined up in a line. And I'm going to do the complement of the ways I can have the 2 boys not together. Okay. So it's almost like your probability. 1, take away the probability of the complement. Okay, I've done the total arrangement, take away the complement of what I need for the question. And it is about 30 odd thousand, isn't it?
It is.
I did all these questions at 5 o'clock this morning. Okay, so there's 30,240 ways that 6 boys and 2 girls can be arranged in a straight line, that the 2 boys are not next to each other or not together. Okay, now also considering this is very having a line where you have a boy at the start and a boy at the end, but it is different to when you have a round table with the separation of the boys around the table. Okay, because the 2 at the end on a round system would be together, but in a line they are not together. Okay, so this is a very thinking and logically thinking, working out, topic. Right, now time for a challenge. Triple I, same question. So 6 girls, 2 boys. Arranged in a row if there are at least 3 girls separating the boys. At least 3. Okay, so this style question, I am not going to use a formula. I am just going to draw a diagram and start considering the possible scenario. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we are considering 8 people in a line. Right, so we need at least 3 girls separating the boys. So I would start working through some scenarios. Now, again, I started this question, I did capital B for boys and capital G for girls. Okay, try not to use that notation because by the time you do all your B's and G's, okay, it's going to take you time. All right, so pick something that's going to be nice and quick to do. Okay, so and I chuckled at this morning. The boys were plus, okay, and the girls were takeaway. So the boys are positive, the girls are negative. And the girls sit there very quietly. Alright, so the question, so this is scenario number 1, okay? So there's a boy at the start of the line. There's at least 3 girls separating the boys. So 1, 2, 3. There's 3 girls next 3 position. Then there is a boy. There's at least 3 girls for that scenario. And then the remaining 3 girls in the remaining 3 places. Okay, that's one scenario. You now need to consider a different one. For 2, you have the boy at the start of the line. Okay, you can have any 4 girls next to, in the next 4 places. Okay. Nope. Nowhere as simple as that. Okay, you then have any 4 girls between those 2 boys, and then the remaining 2 girls can occupy the last 2 positions. Okay, scenario number 3. So, you can still have a boy at the start. We have a possible arrangement there. And at this point, I'm not going to put the minus signs there. I'm just going to consider where the boys are. Okay, so there's 5 girls, then a boy, and then a girl. Alright, boy, then the 6 girls, then a boy. Okay, that is that 4 arrangement where the boy can be at the start of the line. Yes. Alright, can you identify a pattern happening? What's the pattern occurring? This diagonal here. Okay, observe the pattern. So scenario number 5, we've done now all the possible start and finish. So scenario number 5, a girl starts that pattern, and then a boy is second. You then have 3 positions, 1, 2, 3, and then there is a boy there. Okay, at least 3 girls separating the boys. Okay, number 6, you got start and going down the diagonal until you have the boy at the end of the line. There's 3 different ways we can have a boy in the second spot that would meet the condition of that question. 5, 6, 7, 8. So now move the boy to the third position. So we start off with 2 girls. A boy in the third position. There must be then 3 girls following. 1, 2, 3. Then a boy and then the last girl. 8, 9, boy. Boy at the end. Okay, so now your boy is almost taking that same sort of approach down this diagonal. Okay, it might be. Let me just walk through the question first, because I'm not thinking it the same way as you are. You're probably thinking it the same way he is. Right, 6 boys, 6 girls, 2 boys arranged in a line. Yep. At least 3 girls separating the boys. So you then have the boy, you have the first 3 positions considered by the girls, you then have a boy, then the next 3 are girls, and then that means only the last position is a boy. Okay? So, just considering boys and girls, there are 10 ways that can be formed. Okay? Just when you consider the boy and the girl. Okay, now we need to consider the number of arrangements that any 6 girls can be in that spot, any 5 girls can be in that spot, and so forth through your whole scenario there. Okay, so just looking at the boys and the girls, which will be a combination, okay, which we'll be looking at next lesson if you're just considering boys and girls. Okay, but you are now considering the order, then you're considering any of the 6 girls or any of the 2 boys can occupy the first positions respectively, like the first and second position. Okay? So, the way I have worked it out is I have taken this one. So any 2 boys can take that first position. Okay, from that, any 6 girls can take that position. Any 5 and 4 for the next 2 positions. And then the second boy, there's only 1 other boy that can take that position. And then the remaining 3 girls can occupy 3 factorial ways for those last 3 positions. Alright, did we all follow that? What about the second scenario? How many ways? How many ways? How many ways?
4, 3, 1.
Do we notice anything? Can we see the pattern occurring? If I were to multiply everything in both those rows, would I get the same answer? Yeah. Okay, so that means for 10 value, I do this notation on the top row times 10, and I'll have my final answer. Okay, so the arrangement. Right, so I have, for the boys, I have 2 times 1. So I've got 2 factorial. For the girls, I've got 6 times 5 times 4 times 3 times 2 times 1 times 6 factorial. That's for one arrangement of just boys and girls, just considering boys and girls. Okay, we are then using factorial notation to consider specific boys and specific girls, and then there are 10 ways they can do that. Yes?
Don't forget the last times 10.
Okay.
Yeah.
Say it again.
14,400.
Try it again.
6 factorial times 20.
I've got 28,800.
Yeah, that sounds better.
I got 14,400.
Hey?
I got 14,400.
Got 2 squared in my notes. Not 2 factorial. That would be what? Okay, so there's 14,400 ways that can be arranged. 2 factorial. Okay, you grab, get your group, 2 boys. So you grab another, there's 4 of your girlfriend. Line them all up in this scenario. Okay, so we get Robin and Kyle apart from each other by at least 3 girls, and there's 14,400 different ways that can be done. Okay, now I have my approach. Can you now explain anything you might have done differently?
With that one, absolutely nothing.
Yes.
The key really is exactly what happens in that first step. Like when you break it down and you look at what happens inside each of those 10 possible arrangements, that's really straightforward. Okay, and it's just that, you know, well, you've got 6 girls, you've got 2 guys, 6 factorial, 2 factorial. Most people will get that, but it's identifying how many ways that can happen. And one of the things that causes the most problem here is people want a formula. They want to be able to go, plug this in, tell me how many ways that it happens. Now, you can think of it like that, but it's going to take you more time because of the fact that you have to identify the number of ways that it can move, and when you can have them separated by 6, by 5, by 4, and by 3, and then looking at the number of ways that can actually occur as well. So
Exactly what I was saying at the start. Formula based, not so much, okay? Sometimes you just have to draw a diagram, consider your arrangement, do some signs, numbers, identify the pattern, and then write an expression, okay? Would be the much better way to do it rather than considering a permutation formula, okay? So that was pretty much what I was saying. And that means I have had a significant improvement on my permutation combination since I last taught it, last year. Okay, last example. So we looked at an example where they were in a straight line, and I told you if you consider the boy and the boys at the end of the line, when we consider the question that 2 boys were together, okay, they are not together because they are on opposite ends of a row of a line, which is different to when they're sitting around a table, which is what we're about to look at. Alright, so how many ways can 10 people sit around a circular table? What's your expression? What's your expression first?
10 factorial?
No.
Nope. It's already,
Nope.
That would be right if it was in a straight line.
Yes. Hey? Pardon? Depending on your beige for N and R.
Yep.
But I'm going to look at this at a factorial notation.
Best way to think about it, if we put you guys in a circle, right? So we just move 5 to about here. Alright, so we're actually making 5 of us. Okay, so here is one arrangement. Alright, and there are the seats 1, 2, 3, 4, 5. everybody stands up and moves one seat to their left.
Oh, but the name's
Okay,
Oh, no.
now that is not a different arrangement because I am still sitting right between Kyle and Amanda, so that is not a different arrangement to what we are currently in. So what changes then when you sit in a circle?
Okay.
5 factorial?
5, no?
Remember, we've got 10 people.
Oh, wait.
We've got 10 people in this scenario, okay? So let's draw a diagram. Alright, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, don't be scared drawing a diagram, okay? I'm doing this a lot now.
It is the biggest help.
He does this a lot, okay? Draw diagrams, start considering, alright? Now, take that first person. Let's say they're having a meeting, the first person comes in early, okay? And they sit down. Alright, then from the second person coming in, how many different seats can that second person come and sit down? 9 ways. Okay, in other words, 9 seats. The third person comes in, sits down. How many remaining seats are there for that particular person to sit down on? 8. Okay. Now, from that, does it matter where that first person sits in terms of the arrangement around the circle? Okay, so Michaela was here first this morning. She came in, she sat wherever she wanted. Okay. Robin then came in, went to the heater and then sat down. Okay, but from that there are 30 chairs in this classroom. Robin had a choice of sitting down on the rest of the 29. Okay. Now, this arrangement is different to a circle, okay, because you have the rows and you don't have people next to each other at the end, okay? So, the notation will be that first person can sit on any of those 10 chairs, and then the remaining 9 people that come through can sit in a combination of 9 factorial different ways. Okay, because they're arranged in a circle, like I said, if you all stood up, you moved 1 seat to your left, the order is still the same, just how you are sitting around the table is different. Okay, which is different from a straight line because there has to be someone at the start, there has to be someone second, there has to be someone third, right through to someone coming last. Okay? So there are 9 factorial ways they can be seated around a table in terms of the arrangement they sit around in. Did anyone put it in their calculator first? Hang on, did anyone do that? Did anyone didn't do it? You didn't? Did you? Did you put it in the calculator? How many different arrangements are there? Give me a number. Hang on. No. Give me a number. What's 9 factorial? Estimate.
Think about what you got last time when you looked at, well, that was only 6 factorial by 2 factorial. And that was multiplied by 10.
100,000? Have you put in the calculator? 362,880 different ways that can be done. And don't forget, if they were standing in a straight line, it'll be 3,628,800 ways they can stand in a straight line.
Now, that is probably the other way to consider what you look at there. Alright? Your initial reaction here, when Mr. Lee wanted to know how many was, there's 10 people, so it's 10 factorial, right? Okay, other way to think about it, how many ways can we keep that arrangement? If you think about how many times you can turn the people or how many places you can move them, how many ways can you move them around the circle? It's 10, isn't it? Okay, because we can just effectively like shift everyone to the left once, twice, 3, 4, 5, all the way around to, and when we've done it 10 times, we're now back at the start. which really means you can also consider it as 10 factorial over 10.
Technically, yeah.
10 factorial over 10 simplifies back to 9 factorial as well, okay? It's just a different way to consider it, all right? Effectively,
yeah.
they will teach it in both ways, is that you can either lock the first position, which then gives you the 1 by 9 factorial, or you can look at it as the number of people divided by the number of rotations you can go through, and the number of rotations is based on the number of people you have.
And we'll get to that point in the next couple of examples, okay? Now, the next part of the question, if seating is random, what's the probability? Okay, so we're going to consider the difference between arrangement and probability, okay? So, the probability that 4 particular people sit together. Okay, so the probability 4 sit together. Right, so first, how many ways can those 4 people sit together?
Oh, wait.
Well, how many, if there were 4 seats, okay, and they're sitting together,
24. 4 factorial.
keep it nice and simple, 4 factorial. Okay, if you show this, your factorial notation, and you put it incorrectly in the calculator and put a incorrect answer, but you have shown the correct factorial notation, you're going to still get your full marks. Okay? But only if you then show the evidence that you understood that scenario. From those 4 people now sitting together in 4 factorial different arrangement, the other 6 come in and they sit in the remaining 6 places. How many arrangements are there with those people? Isn't it 6 factorial?
Oh, of all together with them?
Yep.
Yeah, all together with them, there is now 6 factorial because you've got the 6 extras plus your group of 4, which effectively gives you 7 to consider, which then when you look at it around a circle becomes 6 factorial.
Okay. Over, how many ways can they be seated around the table? So let's put 9 factorial then. Okay, probability, total number of arrangement, and on top of the fraction is the number of favourable outcomes. We should simplify to 1 over 21. Okay, there's a 1 in 21 chance that 4 people, specific people around a table can sit together. Okay, now, 2 more questions. Right, so the next formula. Okay, the number of different ways of arranging an object, which A of the object are of one kind, B object of another kind, C of another kind, so forth, is given by n factorial over A factorial, B factorial, C factorial, ... And that was the point Mr. Smith made that I was getting to. Okay, now let me illustrate this with an example. F. We have the word thereafter. Okay, 10-letter word, thereafter. Okay, the question asked you how many ways can the letters in that word be arranged. Okay, now looking at them individually, how many different arrangements are there? It's exactly the same as having 10 people in 10 positions on a line. 10 factorial, alright? The arrangement, 10 factorial. Now let's look at the specifics of this. Does anyone notice anything in the letters of that word?
Some of the letters are the same.
So if you had two of the E's, for example, and they swap places, does it change the word? No. Right? So we have to then consider the reduction of that. So you then consider on the bottom of the fraction the number of repeating elements you have. Alright? So the letter E, how many are there? Alright, 1, 2 and 3. So the number of ways those 3 letters can be arranged is 3 factorial within the 10 factorial. Okay, are there any more multiple letters? Okay, how many ways can that R be arranged within the 10 factorial? 2 factorial. Okay, so which is 2, but get in the habit of saying 2 factorial. Okay, because then you don't want to say 3 for this one. Okay, so from 10 factorial, there was...
The T as well.
Oh, this is what happens when you do it at 5 o'clock in the morning. Miss some. Times 2 factorial. Alright, so if we were just looking at individual letters, there was over 3.5 million ways that can be arranged to form a word. Okay, but because there are repeating letters, that does reduce the number of possible arrangements you have. So I've got to divide my answer by 2 now. 151, 200. So over 151,000 ways we can arrange the letters of that word, including the doubled or tripled up letters. My thought precisely last year. G. Alright, Morse code. We're all familiar with Morse code. We know what it is, we don't know how to use it. Alright, basically communication device, dots and dashes. Alright, so in Morse code, how many arrangements are there of 3 dots and 2 dashes? So you have 3 dots, 2 dashes. Okay, so first, how many ways can, if we treated them individually, how many arrangements are there? 5 factorial. Excellent. Okay, get used to saying that, writing that down. Alright. Right, how many? Now we have to consider anything that repeats. So again, if I change the order of 2 of those dots, it doesn't change that order. Okay, because you still got the same outcome as what you had previously. So what would I be writing on the bottom of the fraction? Excellent. Okay. Now, before everyone leaves, because I only got 9, can everyone please now write down the 10 possible arrangements? Go. Well, somehow I only got 9. I can't work out which 10th one.
Right. Oh, so like, can they be next to each other?
You're missing dot, dot, dash, dash, dot.
Dot, dot.
Dash, dash, dot.
There you go. Dot, dot, dash, dash, dot.
Yep.
Got it.
Because you didn't do it in the pattern.
I kind of did. I considered 3 dots and then moved that in each time, and then after I moved that bar in.
I would have then done all my arrangements of 2 dots.
True, yeah.
You got it here. Dot, dot,
Yeah.
dash, dash, dot, but you must have missed one of the other ones there.
Yeah, funny.
So you go searching in there.
Yep.
But yeah, that's what I would do, is go all your 3s.
Yep.
And there's only one in. And then do all of your 2s.
Yeah.
And go
Yep.
that way. It just makes it easier.
So the reason why I've asked you to do this is because if one, you don't understand the application of factorial notation, that's what you need to do. You need to start drawing diagrams and you need to identify a pattern and repetition and come up with an answer, or we consider them as a factorial notation arrangement. Okay, so when you've done that, exercise 13.4 can be attempted, and we'll be looking at combinations on Friday morning.